Hello everybody, and welcome to exercise 4 on page 41 of the workbook. Let's take a minute to read this question together. So, a jogger is running along the side of a straight east-west highway. Her displacement in meters from her home is given by s of t equals 3t cubed minus 0.2 t to the fourth, where t is measured in minutes. Notice that we've got a graph of that function over here to the right. And they give us one other piece of information. Positive values of s of t indicate that she is east of home, and negative values of s of t indicate that she is west of home. Okay, so let's start by maybe labeling units and just thinking about the situation here a little bit. So on the horizontal axis, we've got t. That's being measured in minutes, it looks like. Okay, and s of t is representing a position in meters. Okay, and just to remind you, there's kind of a meaning to positive and negative output values. So we're talking about distances east of home up here, above the t-axis, and west of home down here. And we'll kind of keep that in mind as we're working through the problem. Okay, so let's get started here. So part A asks us to explain in words what the first and the second derivatives of our function mean. Okay, so this is an opportunity to kind of think back to some of these interpretations of derivatives that we talked about earlier. Okay, let's start with the first derivative. Okay, well, if you think about this graphically, the first derivative is about finding the slope of a tangent line. And so if we want to explain this, maybe a good first step would be to think about units. What would the units of the first derivative be? Well, since the first derivative represents a slope of s of t, its unit should be meters per minute, rise over run. So ask yourself, what kind of stuff do we measure in meters per minute? Well, we're really talking about a velocity when we have those units. Okay, so s prime of t gives the velocity. Okay, of the runner in meters per minute. Okay. Well, what about the second derivative then? Could we explain that? Okay, well, the second derivative is about the rate at which the first derivative is changing. Okay, so what quantity measures the rate at which a velocity changes? Okay, if you think about it, the rate at which velocity changes is acceleration. We've talked about that earlier a couple of times. So s double prime of t gives the acceleration. What would its units be? Okay, well, since it's a rate of change of velocity, it should be meters per minute, which would be meters per minute squared. Meters per minute squared. Okay, so there's kind of a roadmap. Some of the questions that they ask us here, we're going to need to make use of these derivatives, and just having in words their meaning might help us just navigate through this problem. Okay, so let's move on to part B here. So they'd like us to find the velocity of the runner at t equals 13 minutes. Okay, well, how do we do that? Well, it might be helpful to remind ourselves what we noticed up above in part A. The first derivative is the velocity, and so this is really asking us to find the first derivative at t equals 13. Okay, so we need to start by finding the derivative. So our function is sitting up here. We need to take its derivative. And notice that what's involved in our function are powers, t cubed and t to the fourth. Those are constant powers of t. So we should be able to use the power rule to find our derivative. Okay, so s prime of t is going to be 3, and then times the derivative of t cubed. Remember how the power rule works. We're going to bring the power down, decrease the power by 1. Oh, whoops, not 3, 2, sorry. Okay, so we're going to get 3t squared for the derivative of t cubed. All right, and then moving over to the next term, we've got a minus 0.2, and then we need to take the derivative of t to the fourth. By the power rule, that's going to be 4t cubed. Bring the 4 down, decrease the power by 1. Okay, and we can simplify that a little bit. So 3 times 3 is 9t squared, and then minus 0.2 times 4 is minus 0.8. Okay, there's our formula for the derivative, and we're interested in the derivative at the number 13. Okay, so we're going to substitute 13 into that formula that we just found, and that should give us the velocity that we're interested in. Okay, and I'll leave it to you to confirm my algebra here. So you'd go to your calculator, and this winds up being about negative 236.6, and we know from above that the units on velocity were meters per minute. Okay, so there's our answer to part B. Okay, now I want to just throw a question out. We've actually finished the question, but notice that we got a negative number here. Can we get a negative velocity? Does that make sense? If you think about it, it's okay for velocity to be negative. That's just an indication of direction. If we look up at the top on our graph for a minute again, t equals 13 is maybe about here. And if you draw a tangent line there, notice that its slope is negative. That's why we're getting a negative number. It just indicates that the runner is running to the west at that particular time. Okay, so let's move on then to part C here. Part C would like us to find the acceleration of the runner at t equals 10 minutes. Okay, well again, looking back at part A, we found that s double prime of t is what gives us acceleration. So we are really looking, oh, not 13, sorry. We are talking about s double prime of 10 here. Okay, so we need the second derivative, and then we're going to substitute in t equals 10. All right, so we might start by reminding ourselves what the first derivative is. 9t squared minus 0.8t cubed. We need to take its derivative. Okay, so s double prime of t is going to be 9, and then we'll use the power rule on t squared. So we're going to get 2t to the first from that. Okay, and then we come to t cubed, take its derivative. By the power rule again, we're going to get 3t squared out of that. And let's go ahead and simplify again. So 9 times 2 is 18t, and then 0.8 times 3. What are we going to get there? 2.4? Okay, so 18t minus 2.4t squared, and unit should be meters per minute squared. We're interested in the acceleration at 10, so let's go ahead and substitute in 10 and see what we get for a numerical answer here. Okay. Again, you might be able to do that in your head, or you can go to your calculator. This turns out to be about negative 60, and again, those units are meters per minute squared. Okay, there's our answer to part C. Okay, and finally, let's see, what's the last part asking us? So they'd like us to graphically estimate the times when the velocity of the runner is 0. Okay, and then use calculus and algebra to find these times exactly. Okay, so let's remind ourselves again of the graphical meaning of velocity. Okay, if you scroll up again here, the velocity way up at the top of the page here is s prime of t. That's the slope of the tangent line. Okay, so do you see any places on the graph where it looks like the slope of the tangent line is 0? Okay, let's clear a little clutter away here. I see one right here, and what would you estimate that time is? Maybe around 11 or something like that? So that would probably be an estimate of one place that the velocity is 0. Are there any other places where it looks like the velocity might be 0? Okay, if you look really closely, the graph looks pretty flat over here, so maybe in the vicinity of 0 might be another place where the velocity is 0. Okay, so those are our guesses. It looks like we've got maybe 2 places where the velocity is 0. Let's see if we can confirm that algebraically. Okay, so finding a 0 velocity is like saying we'd like to know when the first derivative is equal to 0, and so that's going to be our starting point. So we will take our formula for the derivative. That was sitting right up here near the top of the page. 9t squared minus 0.8t cubed. Okay, that's the equation that we need to solve. And just thinking algebra here, I notice that we can factor a t squared out of that. And by factoring, that allows us to split this into two pieces, basically. So we've got either t squared equals 0 or 9 minus 0.8 t equals 0. And let's see, if you look at the first piece, the t squared equals 0, if you take the square root of both sides, you just get t equals 0. That confirms one of the graphical guesses that we made above. We guessed that the velocity looked to be about 0 at 0. What about the other equation? Well, if we add 0.8 t to both sides and then divide both sides by 0.8, let's see what we're going to get here. 9 over 0.8 equals t, and you can confirm with your calculator that 9 over 0.8 is 11.25. Okay, again, we made a guess that it looked like the velocity was 0 around 11. Now that's reasonably close to 11. Okay, and so we would conclude then the velocity is 0 at 2 times. T equals 0 minutes and t equals 11.25 minutes.